Have you ever wondered what we would see if we could travel at the speed of light? This is a question that has fascinated scientists, philosophers, and dreamers alike for centuries. But what does it actually mean to travel at the speed of light? The speed of light is a kind of cosmic speed limit. It's the fastest that anything in the universe can move, clocking in at an incredible 670 million miles per hour. This is such a mind-boggling speed that it's hard to even comprehend. To put it into perspective, if you were to travel at the speed of light, you could circle the Earth about 7.5 times in just 1 second. But here's where things get really interesting. According to Einstein's theory of relativity, nothing in the universe can travel faster than light. So, what would happen if you could somehow reach this cosmic speed limit? What would you see? This is what we call the speed of light paradox. The paradox arises because the speed of light is not just a limit on how fast you can move, but also on how fast information can travel. This means that if you were to travel at the speed of light, you wouldn't be able to see anything in the direction you're moving because the light from objects in that direction wouldn't be able to reach you. But it gets even stranger. Because of the way space and time are connected, moving at the speed of light would also distort your perception of time and space. In fact, from your perspective, time would stop completely, and distances in the direction you're moving would shrink to nothing. This is what physicists refer to as time dilation and length contraction. So, traveling at the speed of light would be a truly surreal experience, unlike anything we can imagine. It's a fascinating concept that challenges our understanding of the universe and our place in it. So buckle up as we embark on a journey to unravel the mysteries of light speed. Imagine you're in a spaceship, accelerating towards the speed of light. As you gain speed, the universe around you begins to change due to the effects of acceleration on the perception of light. The Doppler Effect, a change in frequency and wavelength of light, comes into play. As your spaceship accelerates, light waves from stars ahead appear to shorten, shifting towards the blue end of the spectrum. Conversely, the light from stars behind you stretches out, reddening in a process known as redshift. Parallelly, the aberration of light alters the apparent position of these celestial bodies. Stars seem to crowd forward, creating the illusion of a cosmic light show concentrated at the front of your field of vision. These phenomena work together to warp the star-studded panorama of space into a surreal, dynamic visual experience. Acceleration towards light speed would indeed offer a unique and mind-bending visual spectacle. As we speed up, light from different directions starts to behave oddly. This peculiar phenomenon is known as the aberration of light. It's a concept that might seem a bit abstract, but it's actually quite fascinating and has a significant impact on our visual perception. Imagine you're on a spaceship cruising at near light speed. The light from stars in front of you would start to behave differently. Instead of seeing the stars spread out across the sky, they would appear to cluster towards your line of travel. This is because the speed of light is constant for all observers, regardless of their own speed or the speed of the light source. So, as you approach light speed, the light from the stars is still reaching you at the same speed, but from a shifted angle. But that's not all. As you continue to accelerate, the light from the star would also start to change color. Now, you're probably thinking, wait, how can light change color? Well, it's due to something called the Doppler Effect, which we'll dive into in the next scene. But for now, let's stick to the aberration of light. But as we accelerate further, another peculiar phenomenon comes into play, the Doppler Effect. This phenomenon, named after the Austrian physicist Christian Doppler, is something we experience in our everyday lives, often without realizing it. Imagine the sound of an ambulance siren. When it's coming towards you, the pitch seems higher, and as it moves away, the pitch drops. This change is due to the Doppler effect, but how does this apply to light, you may ask? Just like sound, light also has a frequency. When we're stationary, we perceive this frequency as the color of light. However, when we start moving at high speeds, the frequency of the light changes. As we speed towards a source of light, the waves get squished and the frequency increases. This shift towards higher frequencies is known as blue shift. Conversely, if we're moving away from the light source, the waves are stretched out, causing the frequency to decrease. This shift towards lower frequencies is known as redshift. Now, let's imagine we're accelerating towards the speed of light. The stars in front of us will appear blue shifted. They'll shift from their familiar white to a bluish hue. then to ultraviolet, and eventually they disappear entirely as their light shifts into the X-ray spectrum, which our eyes can't perceive. On the other hand, the stars behind us will appear redshifted. They'll slowly shift from white to a reddish hue, then to infrared, and just like the stars in front, they'd also disappear as their light shifts into the radio wave spectrum. But remember, this is not all. As we're moving at near light speeds, the light from the stars will not only change in frequency, but also in intensity. The light from the stars in front of us will become brighter, while the light from the stars behind us will dim. So the Doppler effect adds another layer of complexity to our light speed journey. It's not just about getting from point A to point B anymore, it's about experiencing the universe in a way we could never have imagined. Now here's where things get really weird. As we approach the speed of light, time and space themselves begin to warp. This phenomenon, my friends, is what we call time dilation and length contraction. These are not just fancy terms in a theoretical physics textbook, but actual occurrences that would completely alter our perception of time and space. Let's start with time dilation. This is the idea that time, as we understand it, does not remain constant but can be stretched and distorted. You may ask, how is this possible? Well, according to Einstein's special theory of relativity, as you move faster, time appears to slow down. So if you were traveling close to the speed of light, your watch would tick slower than the watch of someone stationary. You might feel like you've been traveling for just a few hours, but decades or even centuries might have passed on Earth. Sounds like a science fiction movie, doesn't it? But it's not, it's science fact. Now, onto length contraction. This is another strange but true consequence of traveling near light speed. As you speed up, objects in your direction of travel appear to become shorter. Imagine you're in a spaceship zooming towards a star. As your speed increases, that star would appear to get closer, not because you're covering distance at an incredible rate, but because the physical distance between you and the star is contracting. So, what's causing this bizarre behavior? It's all due to the fact that the speed of light is a constant in all frames of reference. No matter how fast you're going, light will always zip past you at the same speed, around 300,000 kilometers per second. This constancy forces time to stretch and distances to shrink, making sure the cosmic speed limit is never broken. But here's the kicker. These effects aren't noticeable at the speeds we're accustomed to in our daily lives. You'd need to be going incredibly close to light speed to experience time dilation or length contraction. That's why we don't see cars on the highway getting shorter or time slowing down when we catch a flight. So let's put this all together. If you were to travel at the speed of light, you'd experience extreme time dilation and length contraction. Time would stretch so much that it would appear to stop altogether, and distances would shrink to nothingness. You'd be in a state of suspended animation, frozen in a moment of time, while the universe outside carries on. In other words, reaching light speed would be like stepping into a cosmic funhouse of distorted time and space. So what happens when we actually reach the speed of light? The very idea is mind-boggling, isn't it? But let's indulge in this thought experiment for a while. According to Albert Einstein's theory of special relativity, as an object moves faster, time around it slows down. This is known as time dilation. You may remember this from the famous twin paradox, where one twin travels at high speeds in a spaceship and returns younger than the twin who stayed on Earth. So if we somehow managed to travel at light speed, time would stop entirely. We would be frozen in a moment while the universe outside would rush by in a blur. But that's not all. There's another strange phenomenon called length contraction. As you approach the speed of light, distances in the direction of your motion start to shrink. Imagine you're on a spaceship hurtling towards a star that's light years away. As your speed increases, that distant star would seem to get closer and closer until, at the speed of light, it would appear right next to you. But here's the catch. Only you would perceive this. To an outside observer, you would still be light years away from the star. Now here's where things get really tricky. Einstein's equations tell us that as an object approaches the speed of light, its mass increases. At light speed, the mass would become infinite, requiring an infinite amount of energy to keep moving. So, according to our current understanding, reaching the speed of light is impossible for anything with mass. But what if we could? Would we see a blur of colors as we zoom past stars and galaxies? Or would everything appear frozen like a cosmic snapshot? We can't say for sure. Our understanding of the universe is based on the laws of physics as we know them, and at light speed, those laws seem to break down. Reaching light speed then would be an experience beyond our wildest imaginations. But is there a way to cheat these cosmic laws? Some scientists believe there might be. Enter the realm of theoretical physics, where imagination meets mathematics and scientists dream of solutions beyond the speed of light. One such concept is the warp drive, a theoretical propulsion system that manipulates space-time itself to achieve faster-than-light travel. The warp drive is not about moving a spacecraft in the traditional sense. Instead, it's about moving the fabric of space-time around the spacecraft. Imagine a piece of paper. Now think of a pencil dot on one side and another on the opposite side. The quickest route between these 2 points is not a straight line across the paper, but rather to fold the paper so that the 2 points touch. This is the principle behind the warp drive, where space-time is the paper and the spacecraft is the dot. The concept of warp drive originates from Einstein's theory of general relativity, which states that massive objects cause a distortion in space-time which we perceive as gravity. Theoretically, if we can create a distortion in space-time, we can bend it to our will, creating a bubble of normal space-time around the spacecraft and contracting space-time in front of the ship, while expanding it behind. However, the concept of warp drive is not without its challenges. One of the main issues is the amount of energy required. Current calculations suggest that warping space-time to a significant degree would require energy equivalent to the mass of an entire planet converted into pure energy. That's a tall order by any standards. Furthermore, even if we could generate such immense energy, there's a problem of stability. The creation of a warp bubble might trigger uncontrollable fluctuations in space-time, which could be catastrophic. Then there's the issue of time. If a spacecraft could warp space-time to travel faster than light, it would essentially be traveling back in time, according to relativity theory. This introduces a whole new set of paradoxes and complications. Yet despite these hurdles, the concept of warp drive continues to fascinate scientists and science fiction writers alike. It represents a potential solution to one of the greatest challenges in space exploration, the vast distances between stars. If we could master warp drive technology, we might be able to traverse these distances in a fraction of the time currently possible, opening up the cosmos for exploration and perhaps even colonization. While warp drive remains in the realm of science fiction, it's a tantalizing glimpse into the possibilities of future space travel. So, what would we see at the speed of light? The truth is, we simply don't know. We've explored the paradox of light speed, the curious effects of acceleration, and the aberration of light. We've delved into the Doppler effect, time dilation, and length contraction. We've even touched upon the tantalizing theory of warp drive. Yet, at the end of it all, we're left with more questions than answers. The speed of light, it seems, is a cosmic enigma that continues to baffle and bewitch us. It's a testament to the uncharted territories of science and a reminder of how much we still have to uncover. Scientists around the world are tirelessly working to decode its mysteries, pushing the boundaries of our understanding. In the meantime, the speed of light remains one of the greatest mysteries of our universe, offering endless fascination for those who dare to ponder its depths.